Welcome everybody to today's video. In today's video, I'll be explaining the action potential. First of all, I'll begin with where and how the action potential is triggered. And back to this picture. I'll not explain it again. You can watch the video if you want. I'll just say that here in the postsynaptic neuron, okay, it's the same as this one. This neuron is the postsynaptic neuron. As I said in the last video, the postsynaptic potential is formed here, right? Okay, it can be either IPSP or EPSP, inhibitory postsynaptic potential or excitatory postsynaptic potential. Inhibitory postsynaptic potential will never lead to an action potential, right? On the other hand, excitatory postsynaptic potential may lead to an action potential, may not. So it can be either just a graded potential or lead to an action potential, which is AP, action potential. Okay. What is a graded potential? What is an action potential? We need to know that when we're gonna draw the graph, it looks like this. Here we have the time on the x-axis, and on the y-axis we have the membrane potential, which is basically the voltage difference between the inside and the outside of the membrane, here and here. All right. And in the case of neuron, in the relaxing state, we have minus 70 millivolts. All right. So here we have millivolts. Minus 70 millivolts. Why do we have this voltage difference? Because on the outside we have a positive charge, and on the inside we have a negative charge, and this is, as I said, in the normal state, in the relaxing position. Okay. And the minus sign here indicates the charge on the inside. I mean inside the cell, or in the on the inside surface of the membrane of the cell. Okay. This is the minus. And we have a really important concept here called the threshold. This is the threshold. What is a threshold? We know that not all local depolarization events produce action potentials. The depolarization must reach threshold values if an axon is to form an action potential. Okay, so the membrane potential has to reach this value, the threshold, in order to fire an action potential. Okay, and now I'll explain these stages. What is a threshold? One explanation is that the threshold is the membrane potential at which the outward current created by potassium movement is exactly equal to the inward current created by the sodium movement. Okay, so the current by potassium is exactly equal to the current by sodium, and it's an unstable state. The equality here, okay, is not the relaxing state. It's not the normal state. Potassium has to be more, okay. The current has to be higher in potassium movements than by the sodium movement. Threshold is typically reached when the membrane has been depolarized by 15 to 20 millivolts from the resting value. It depends on this number, the threshold. It could be higher or lower, minus 65 for some neurons. Okay, this depolarization, the depolarization means up and the polarization means down. Okay? But we call the down one a repolarization if it had already gone up. So then it's a repolarization. So this we call it repolarization. But I'm not explaining this now. Okay, just to be familiar with depolarization and repolarization. So the depolarization status represents an unstable equilibrium state. Okay, the depolarization. So when Na goes in, okay, I draw a misleading drawing here. It should be like this. So this is an axon of a neuron. We have potassium inside more than outside, and a sodium outside more than inside. Okay. So when sodium ions go in the neuron, okay, we have a depolarization. And this represents an unstable equilibrium state. If we reached this level, okay, now it's really important. If one more sodium ion enters, further depolarization occurs, opening more sodium ion channels and allowing more sodium ions to enter. So if here in this state, if one sodium ion here, only one enters, so we have an action potential. But in this state also, it's the same state. It's the same level, the threshold one. If, on the other hand, one more potassium ion leaves, okay, so then the potassium, that means that the potassium is producing a little bit higher current, and this is a normal state, okay? The membrane potential is driven away from the threshold like this. So it will go to minus 70. It will go back to the minus 70, okay? So this is the difference. And here we call it graded potential. But this one is an action potential. All right? And now you can understand the difference. I wrote here EPSP. It can go to an action potential or graded action potential or graded potential. So the graded potential is like this only. An action potential is like this. All right? Okay. Now I can go to explain each part of the action potential. Here, 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 and here. But before I move on, I need to clarify something about the graded potential. I said that here, at this level, if one more potassium ion leaves, the membrane potential is driven away from the threshold here. But how does that happen? How does the membrane potential go back to its normal state, to the relaxing state level, to minus 70 millivolts? How? Because here, if one potassium, okay, goes out, then sodium channels will close, and potassium channels will continue to diffuse outward until the potential returns to its resting value. And it actually makes sense. Why? Because we know that this sign is for the inside, right? This is the inside, and this is the outside. Here, at this point, uh, at this point, if potassium, which is positive, goes outside, so the negativity on the inside will go higher and higher and higher as potassium ions continues to go by passive diffusion to the outside. The negativity will go higher. So look, as we go down from minus 55 to minus 70, the negativity is being higher and positivity is lower. So that makes sense. That makes sense. That potassium out means polarization. Remember, polarization and depolarization. Don't forget these two words, okay? And it will diffuse outward until the potential returns to its resting value. So now we know that the excitatory postsynaptic potential, when it is triggered here, it will go here to like go and continue until it reaches the axon hillock, okay? Where the action potential is triggered. If it was strong enough, it will reach the axon hillock, and an action potential will be triggered. If it's not strong, it will decay and there's no action potential. I'll illustrate it here. So this is the postsynaptic neuron. Here, the great potential is formed here or here, in the dendrites or in the cell body. So we'll go here, 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 here. If it reaches this area, this is the axon hillock. Okay? If it reaches this area, and if it was strong enough, then an action potential will fire and will propagate until the end. And maybe here there will be another neuron, which will be the postsynaptic neuron in this case. But we will discuss the propagation in another video. Now we are focusing on the stages of the action potential. Okay. Okay, guys. To simplify it, I have this drawing. Okay. Let's begin. First of all, we have the resting state. What is the resting state? In the resting state, you need to know that this one is the sodium voltage gated channel. This one is the potassium voltage gated channel. Okay? But this one is the sodium potassium pump. It also contributes in the action potential. Okay? So in the resting state, the voltage channels, gate channels for sodium are closed, as well as potassium. And we have leakage channels for sodium and potassium, which are open all the time. Sodium, potassium, sodium goes in, potassium goes out, and there's some kind of movement. I can explain it later. I can also explain how these ions concentration differ. As you know, here we have negative on the inside and positive on the outside. You can ask, why is it negative on the inside, although we have positive potassium ions? That is because we also have negatively charged anions, proteins, okay? And here it is positive, although we have chloride ions, negative chloride ions, okay? But because sodium ions are more concentrated as well, these proteins, that's why we have positive on the outside and negative charge on the inside. And the resting state is, as we can see here in the graph, it's minus 70 millivolts. Okay? So now, what breaks this resting state? What happens? What happens here? I talked about this stage. This is when some, not a lot, some of voltage gated sodium channels open and a few sodium ions will go in, right? When it reaches this level, if only one sodium ion goes in, then we have an action potential. And of course here, since sodium is going out, this activation gate will be open, as well as this inactivation gate. These are the names of the gates. But I'm not concentrating on these now. I'm just trying to explain the movement of ions, okay? So, after reaching the threshold and one sodium ion goes in, we have an action potential. Why does it fire? Why? Because a huge number of sodium voltage gated channels open at this stage. And a large amount of ions, sodium ions, penetrate to the inside. Okay, so now as these sodium ions are going inside, the positivity of the inside is becoming higher. The negativity is becoming lower. Okay, that's why we are going up. Depolarization. Depolarization is caused by sodium ion flowing into the cell. Depolarization. The negative charge is becoming a positive charge or less negative. Okay? To reach plus 30. When it reaches plus 30, what happens? we have the repolarization. By the way, what do these numbers mean? What does plus 30 minus 70 mean? So, what is 30? 30 is the membrane potential, we said. What is membrane potential? Is the voltage difference between the inside and the outside. So, since the positive and negative signs indicate the charge on the inside of the membrane, okay? So, here, plus 30, which is the maximum level, means that the inside is 30 millivolts, since the y-axis unit is millivolt, 30 millivolts more than the outside. And the resting state minus 70 millivolts. This means that the inside is 70 millivolts less than the outside. This is just for clarification, just to know what do these numbers represent. So now, re repolarization is caused by potassium ions flowing out of the cell. So now, here, sodium gated channels will be closed by this thing, which is the inactivation gate, and potassium channels will open, and ions will go out to make the balance, to go back to the resting stage. So when potassium ions go out, we have an increase of positivity outside, right? And a increase of negativity inside. And this is the important thing. We have an increase of the negativity because the resting state, the normal state, is that the inside of the membrane is negative, right? Is more negative. So by increasing the negativity, we are going back to the resting state, repolarization. It's actually a polarization process, but we call it a repolarization because of the depolarization before it. So it is depolarization and then the prefix repolarization. Okay? But here, we don't have an inactivation gate. Okay? So we have some kind of delay, which caused a hyperpolarization, hyper. Maybe you heard of hyperglycolytic or something. Hyperproteinemia. Hyper means excessive. Okay, so hyperpolarization is caused by potassium ions continuing to leave the cell. Why? Because of a delay to close these gates. So we notice that sodium gated voltage channels close faster than potassium ones. Okay, that's why potassium ions continues to go out, and the membrane potential actually doesn't stop at the resting state. It goes even further down, and this we call it hyperpolarization. And we need to bring now the membrane potential up again. How does this happen? But before I talk about that, I wanted to mention relative refractory period and the absolute refractory period. I will do a separate video for these. That will be a short video. I think I should talk about it separately, okay? But I'll just like say briefly that this is the refractory period, the absolute refractory period, and this is the relative refractory period. In the absolute refractory period, sodium voltage channels are opened. Here, sodium voltage channels are closed. Here, in the absolute refractory period, no other stimulation is possible. But here, if the stimuli was really, really strong, so another stimulation could happen and action potential could fire from the relative refractory period. But I will dedicate a separate video for these two concepts, okay? Guys, at this point, the potassium gate channels will be closed as well as the sodium. Then the activation will be closed, but the inactivation will be open. And I will explain how do sodium channels, gated voltage channels, change their shape in order to suit the process of the action potential. I'll explain it in a separate video. And please write this in the comment if you really want that video about the sodium voltage gated channels. Okay. In the hyperpolarization, after the hyperpolarization, how does this happen? How does the membrane potential go back to the to minus 70 millivolts, to the resting state? This sodium potassium pump is really important because after sodium went in and trapped in, so it accumulates in, and potassium went out. So here we have a lot of potassium, a lot of sodium, but we need to do the resting state. We need to go back to the normal state, okay, to the normal concentration of ions. A lot of sodium out and a lot of potassium in. And now with a better look, these sodium potassium pumps, which actually use ATP. But I'm not gonna explain this now. I may explain it later because I'm now focusing on the ion movement. Okay, so let's talk about this pump, for example. It ejects 3 sodium from the cell and then transports 2 potassium ions back into the cell. So these sodium ions will go here, and then the pump will change its shape in order to eject 3 sodium ions out. So now these pumps are trying to solve this problem, accumulation of sodium here inside and potassium out, by ejecting 3 sodium out, and then after this 2 potassium ions will go here, here, and here, and the pump will change the shape again in order to transport these 2 potassium ions back into the cell, so to the inside, like this. And these potassium will go back inside. And this process continues. So another 3 sodium will go here, and another 2 potassiums will go here, there, and then back here. Okay, so this process is the main process that help the membrane potential to go back to the resting level here, minus 70 millivolts. If you're watching till now, so good job, you're amazing. It's really a long story and a complicated story. I tried to simplify it, and I think I did, hopefully. And there's a lot of things that I didn't talk about, like the active transport and the passive transport. How does this sodium gate active, inactive changes during the action potential? So I'll not like do them in one video, in one long video. It's better to separate them, okay, in order to focus on the points one by one. So that's why I'm gonna do another video regarding passive and active movements, ion concentrations, this gates changes, okay, and also I can do one with what types of channels we have and where we can find them, okay. Thanks everybody for watching this video. Don't forget to hit the like button and subscribe for more. You could also write what you want me to explain, what topic you want me to explain in the other video in the comments. Okay, see you in the other video, everyone.